Thanks for the opportunity to talk here. Driving into work today, taking my 5-year-old daughter to her preschool at Stanford, usually when I tell her I'm going to a meeting, her reaction is, "That's very boring," and she offers to hand me a potato for reasons too complicated to explain. But telling her I was going to a meeting about people who want to use giant lasers to send spaceships with sails to the nearest star to look for other planets, she was willing to admit that that was actually a pretty cool job for somebody to have. So we should all remember, people know that I tend to be somewhat on the cynical and skeptical side, but it's nice to be reminded that we actually do have a pretty amazing job and that we can talk about things like this in a professional context. The work I'm going to present, and really an enormous amount of credit for not just this presentation, but the fact that we're having this discussion at all, should go to Russ Belikov, who's been a long-term passionate advocate of the idea that Alpha Centauri is a special system that we can study in a level of detail that most stars don't get lucky enough to be able to study. And so a lot of slides come from Russ and his collaborators, including Eduardo, Tyler, and so on. For the Starshade, a lot of the credit also goes to Simone and Adam in the Aeroastro department, who've been thinking about how we could actually do this for real at a reasonable small cost. Usually it's a bad sign when people giving talks mention Galileo, let alone compare themselves to Galileo. But since Avi did it, I figure I'm allowed to mention Galileo once more. This is just a cool animation showing, of course, his observations of the satellites around Jupiter. And in the history of our understanding of the solar system, this was a pretty pivotal moment. The proof that Earth was not the center of the solar system came from astrometry, came from the measurements and the fits that Tycho and Kepler did. But it's interesting to note that the visual demonstration, looking and seeing that something was going around something other than the Earth, is what was so compelling that it persuaded the church to lock Galileo up and treat him as a heretic. So there's something about images as opposed to wiggles on a graph that is important to the imaginations of people. And the same thing has happened in direct imaging of exoplanets. Of course, it's hard. We always like to say looking for an extrasolar planet is like a lighthouse looking for a firefly next to it. I will correct that in a few more slides. But it's been done for a handful of systems. And these images that didn't exist 10 years ago are a beautiful window into other solar systems. My favorites, not that I'm biased, of course, is HRD 799, the system Christian Meroy discovered. 4 young supermassive planets orbiting around a young, somewhat more massive than the sun star. Christian put this video together showing data from 2008 to 2013, where you can see the planets. You can easily see 3 of them. The 4th one's a little hard to see orbiting. They're obeying Kepler's laws. The one close to the star goes fast. The one far away from the star goes slowly. That is not a surprise. We expect Kepler's laws to be universal. But the fact that we can see it for real from outside, as opposed to just in a computer simulation in our lifetime, is really pretty awesome. And those of us with next-generation systems are working very hard to find planets that will complete their orbits in, say, 10 years, so we can actually make the whole movie in a reasonable timescale. Equally with direct imaging, the fact that you can see planets means you can see light from them, and you can extract spectra. Here's the 51 Eridani planet discovered by the Gemini Planet Imager, in the ways that tell you things about their real composition in a way that transits, except in ideal cases, or astrometry don't. It's levels of knowledge going beyond what you get from individual planet detections. In this case, individual bumps and wiggles in the methane spectra fit to models can allow us to measure atmospheric composition, surface gravity, say something about cloud structure on the presence of the planet, and hints about its formation mechanism. So what we want to do, of course, is not these for the easy cases, but the hard cases. I mentioned that imaging a planet is like looking for a firefly next to the lighthouse. In fact, the ones I've just shown you are the easy ones are fireflies next to lighthouses. Earth-like planets are like looking for bioluminescent algae next to a lighthouse. In addition, in a typical case, if the bioluminescent algae or firefly is 5 feet away from the lighthouse, it's like you're looking for it in Nashville. That's challenging. But Alpha Centauri is only in Reno. And so that's within the regime where we could begin to imagine that it might actually be detectable. As lots of people have said, a special thing about our sun is that we have this solar-type star next door. Not easy, but at least possible. This figure, also put together by Russ, is sort of a summary in plotty areas, maybe too late in the day for plots, but of how hard this is and where we are now. The plot shows contrast, ratio of star brightness to planet brightness versus angular separation. It shows the real known extrasolar planet systems moving from early generation instruments to SPHERE and GPI, the 2010 current coronagraphs. And then it shows where Earth-sized planets around all the stars in the solar neighborhood would live. Jared will talk about this sea of planets close to the stars, the ones that are orbiting M stars that are both very bright but painfully close, but maybe within reach of the ELTs. Next generation space telescopes in the 2020s will reach this sensitivity for a larger sample of planets, but right now, small telescopes, 30 and 45 centimeter telescopes, could get into the Alpha Centauri detectable planet regime. Just showing again in projected geometry the habitable zones and the geometries of the system. I don't think I'll talk through it in lots of detail, except to say the inner circles, this laser pointer's not doing much for me, the white inner circles surrounding A and B show the inner working angle, the closest geometry at which you could hope to see a planet. The shaded regions show the habitable zones, the places where planets would live. Most of their time, planets spend their time outside of the inner working angle where they could be detected, depending on the orientation of the system. But if, for example, we've flown an astrometry mission beforehand, we would actually know when the planet is going to be doing that, when it's going to be peeping out past this inner working angle in a way that would make it possible to imagine a short duration mission successfully finding planets. We separate planets from starlights. Lots of people in the room are experts in this. I'll just show one or two slides of it in two ways. The first way is a coronagraph. So here's a star. Here's an image of a star seen through a telescope full of little bright rings. You put a mask in to block the star. A little bit of light diffracts around the edge of the mask, and you block that again downstream, and this diffracted area pattern goes away. The details of how it, with modern technology, are extraordinarily complicated. These masks can involve complex phase and amplitude patterns, nanoscale features, but you can remove the scattered light from a star to a point where you could potentially see a planet to an angle that's set by sort of the wavelength over the diameter of the telescope at the cost of throwing away a lot of light. The planet, of course, misses the mask, goes through all the optics, and so it's visible. And so Russ, as well as others, have been advocating a version of this dedicated to look at Alpha Centauri, taking advantage of how close the star is to do it with a small telescope. A version that was proposed to the NASA Explorer program that's shown here would have a 45-centimeter off-axis telescope, an advanced coronagraph based on designs by Olivier and others. You still need adaptive optics, even though you're in space, because you have to correct for small aberrations in the telescope that would scatter light and hide the planet signal, but we know how to do adaptive optics. And you could see planets down to sort of 0.4 arcsecond scale. The process of working your way down in contrast from the 10 to the minus 2 signal that you just get with an ordinary telescope to the 10 to the minus 10 signal of the planet is complicated, but not impractical. A mix of using the deformable mirrors to remove the light from not one but both stars, which is a complex problem that Russ's group has looked on, very long exposures, and then taking advantage of the motion of the telescope and the motion of the Earth to remove a planet signal from the complicated pattern of static aberrations and artifacts, and then ultimately beating down photon-type noise long enough. Russ's simulations say in principle you could do this with a sort of 30-centimeter class, an 18 by 35 centimeter telescope, especially if you know when to launch it and you're willing to accept a little bit of technology risk. The other approach to doing this is star shades. So if you see a bright, I'm looking at a lot of bright lights. If you were looking at the bright sun and you saw a bird flying next to it, what do? You do not instinctively put in the Leo mask in your eyeball and sharpen the deformable mirror in your eyeball to make the bird detectable. You do this. You hold up your hand to block the sun. So bright thing next to a dim thing, you put your hand in the way and you can see it with an eyeball. Star shades are essentially the same thing, except that rather than your hand, you have a 30-meter diameter in a classic starshade architecture, free-flying spacecraft about not 1 meter, but 25,000 kilometers away from your telescope. The details of why it's that far away and that's large come from optics. The shape actually has to be complicated and feathered at the edge to channel Fresnel diffraction in a way that makes the planet potentially detectable. But people who understand optics know how to do that. In fact, the optical physics is sort of Goodman textbook level stuff that any of us as physicists know how to do. It has the advantage of decoupling the question of how close you can look to the star from the diameter of the telescope. And so it works very well with small and medium-sized telescopes. You can get to 0.1 arcsecond scales with a 1-meter class telescope, which is challenging to do with a classical coronagraph. It's a simple telescope and a high throughput. But what you've done is you've traded physics complexity, the Fresnel physics that we all understand, for engineering complexity. You now have two spacecraft 50,000 kilometers apart that have to maintain their formation at the level of a fraction of a meter. God forbid you have to look at another star, because then you have to move them with respect to each other, which we know how to do, but takes time and fuel. But at least in theory, it's a very nice complement to the direct coronagraphs. In a general case, it can operate over a very broad range of wavelengths, too, all the way from the ultraviolet to the infrared, with complicated trades, again, based on the Fresnel optics and the geometry of the system. But these large-scale star shades really have to be thrown away from the Earth. They have to go into Earth-trailing or L2 orbits in order to maintain the formation. And that's expensive in terms of launch costs, communications, and spacecraft complexity. The work we've been doing here at Stanford, and Simone and Adam in particular, is to think about a small-scale version. What could you do in Earth orbit? And inspired by various ideas for orbit design, they come up with a geometry where you have two spacecraft in Earth orbit in tilted and highly elliptical orbits. And for about an hour or two every day, way up at their most distant place from the Earth, they align such that the relative motion between the spacecraft is almost all along the line of sight, which doesn't affect the coronagraph. The drift between the spacecraft in the plane of the telescope, the plane you actually care about, can be canceled by something on the order of, it says meter per second, that's a typo, it should actually be centimeter per second. A centimeter per second or two of fuel can keep these spacecraft aligned for a couple of hours every day to make science observations. Then the formation falls apart, you go down to the close pass to the Earth, you fire the thrusters again to reassemble the formation, and they come back together again the next day. With reasonable fuel budgets, you can imagine doing this 50 times in a row, particularly if you don't want to retarget it. It doesn't retarget all that well. And operate with sort of a 2-meter scale occulter and a 10 to 30 centimeter telescope. This is my crazy version of a crazy incomprehensible figure from Adam. You've had lots of crazy incomprehensible figures for late in the day. It's a plot of two quantities, the radius of the occulter along the y-axis, so a 1-meter occulter down to a 10-centimeter occulter, the separation between them. And those quantities determine two things. First, it determines the inner working angle, the angle you can see the planet at. And that's just from geometry. Big occulter blocks lots of the sky. Move it farther away, blocks less of the sky. The lines here sort of show interesting ranges of contrast and inner working angle. The habitable zone lines are shown by the ones I've written words along. You want inner working angles for alpha Cen, 400 milliarc second class. And then the colors show the contrast expressed as with a fraction of the starlight that leaks past the occulter due to Fresnel optics and other optics effects. As you move the spacecraft, make the Starshade bigger, you do a better and better job of suppressing that light. As you move the occulter closer to the spacecraft, which helps the orbit, you do a worse and worse job of suppressing the light. But there's a region you can operate in where you get the kind of suppression we need, 10 to the minus 8, an inner working angle we need for sort of 500-kilometer level spacecraft separations, which is the orbits that Simony and his people know how to do. So there's a spot where this works. An important caveat is that little details, like the roughness of the edge of the occulter, can cause it to leak light. You'd have to manufacture the occulter at about 10-micron tolerances. Small occulters have very tight edge tolerances, but that's not crazy. Manufacturing thing with 10-micron smoothness is not out of the question. Just engineering. I'm a physicist. I'm allowed to say that. The design studies we did in detail were for a 10-centimeter, a CubeSat telescope hooked up to a microsatellite 2-meter diameter occulter. There's lots of science and engineering that does, but not planets around Alpha Centauri. So you probably need to scale up to a 30-centimeter class microsatellite telescope. Not wholly coincidentally, Peter just talked about a 30-centimeter telescope. The Coronagraph talked about a 30-centimeter telescope. There's room to imagine a family of common 30-centimeter microsatellite telescopes that would do a series of these science missions. Also, not coincidentally, it's not that different than telescopes people launch enormous numbers of now to look down at the Earth. So there's a range in which it's a plausible low-cost mission. The physics of the occulter pushes you towards ultraviolet light. That's actually a feature, and I'll talk about why in a second. So why? What do you learn from these? We're not going to do spectra. Tiny telescopes are not going to do spectra of Earth-like planets. We're going to get colors. But colors do tell you something about planets. Simulations by Tyler Robinson. Here's the spectrum of the Earth compared to a cool Neptune, compared to Venus, compared to Mars, and 3 bands that you could potentially study with a small coronagraph. The Earth is distinctively brighter in the short wavelength band. There's a word for that. The word is blue. That's why the Earth is referred to as a blue dot. It's the only thing that's that blue in our solar system. You could imagine things that are that blue in other solar systems. It's really blue because of Rayleigh scattering. In addition to the oceans, you can have Rayleigh scattering from other kinds of clouds if you get the cloud sizes wrong. The other thing the Earth has that nothing else in the solar system has is oxygen. Because it has oxygen, it has ozone. And so with the occulter probing in the UV, you could potentially measure the depth of the ozone feature, which is an unambiguous marker of the presence of oxygen orbiting one of these planets. It's hard. Detector technology and signal-to-noise is challenging to work out, but it's hard in an engineering way that we could at least study. Exposure times vary depending on how good the starlight suppression is. They would have units of days if the designs work the way they're supposed to. So it would take 4 days, equivalent to sort of 50 or 100 passes of the Starshade to make the measurement deep inside the ozone band. Only a day or so to successfully do it at the wavelength where the ozone band doesn't eat the light. A couple of days for the internal coronagraph. NASA is thinking about all these things. So if we're thinking about what we could do with short-term private missions, we should think about the NASA landscape. But the NASA landscape isn't going to start to do anything until 2025. That's the date when NASA will launch its first high-performance coronagraph in the W1 spacecraft. And even that, is going to spend most of its time doing dark energy or something boring like that, rather than looking for planets. Most of my cosmology colleagues have left the room, I think, so I can say that. It will be very powerful for super-Earth-sized planets. It's not particularly designed for binary stars, so it might have trouble with Alpha Centauri, though people like Russ will work to overcome this. W-FIRST may get a Starshade. People like Sarah Seeger in particular are extraordinarily passionate and compelling advocates for the science W-FIRST could do with a Starshade. If that happened, it would be a sort of 2028 timescale with ongoing discussions about risks. The real flagship planet finders are going to fly 20 years from now in any world that the rest of us live in. If we could successfully show that concepts like the Starshade work, that would certainly increase the case for flying it, particularly on the time, if we could do it on the time scale of the next astronomy decadal survey. So there's a way at which doing this with a small mission will teach us in advance of flying the big missions how to actually do it that I personally find kind of compelling. The sort of conclusions, you can watch this awesome movie that Russ's people have put together of a year or two of this mission, watching Alpha Centauri planet's orbit come into focus as the telescope changes its properties. Optical UV spectrometry is a nice way to determine the properties of planets on a scale we can afford. Low-cost missions orbiting Alpha Centauri can actually do some of this, particularly if you do it as a series, if you combine it with the astrometry mission so that you know when you launch it and whether it's worth doing. The optical chronograph and the UV Starshade are complementary. They have different technical risks, but you could imagine, for example, common spacecraft designs, or even a single spacecraft that spends a bunch of its time doing chronography, rendezvous with the Starshade along the ways that Sarah and others are advocating for W-FIRST. And making this picture really would be a revolutionary moment in the history of humanity in a way that very little else would. And I'll stop there and take questions.
What do you have to do with the Starshade to deal with the binary?
So what you would do with the Starshade to deal with the binary, you can do more than the chronograph, is polish the heck out of the primary mirror. So if you could polish the primary mirror down at about 2 angstroms, and you can buy mirrors like that from Tinsley if you have a big checkbook, and take advantage of the fact that it's far enough off axis to use a chronograph, you can get the light of the secondary star below where you need it to be. And I actually I spent some time today running simulations on my laptop, so I can show you a few cases of that. So it's not trivial. It'll drive the cost of the mission up, but it's certainly not impossible. The chronograph, as you know, of course, Russ has worked a lot at wavefront control. Or you do the twofer, which is you fly a mission with a chronograph and a Starshade, and the chronograph kills one star and the Starshade kills the other.